In this lecture, we're going to talk about emission and absorption spectra and how they contain or encode details of the chemical composition of stars, as well as containing extra information about the mass and radius of stars.
Here's the sun spectrum. We saw the spectrum that is filled in red last week. It's the sun spectrum taken at the surface of the Earth. That means that a lot of the sun's light has been absorbed in certain wavelength bands, resulting in these big chunks that have taken out of it. If you measure the sun's spectrum at the top of the atmosphere, you get the yellow spectrum here. This and the grey smooth spectrum is the best black body spectrum fit to the sun spectrum. So last week we talked about black body spectra. They are often called continuous spectra because the intensity of light emitted at a particular wavelength when plotted forms a continuous function. There are no sudden spikes or dips. The sun's actual spectrum on average follows the black body spectrum pretty closely, but it contains lots of spikes and dips as well, kind of overlaid on top of that black body spectrum. So real spectra, although on average follow a black body spectrum, they contain a lot of features that we need to understand. So those features are produced by some fairly simple atomic processes, the absorption and emission of light by electrons in atoms. Taking the Bohr model of the atom just as our picture, we know that electrons occupy different orbitals in atoms. There's a ground state, bottom orbital, and then essentially an infinite number of possible orbitals on top of that. In order to excite an electron up an orbital, you need to give it some energy. And you can do that by absorbing light at precisely the correct frequency or wavelength. Similarly, an electron that has been excited to an orbital above its ground state can drop down again by emitting a photon at a very specific wavelength or frequency. The wavelength of light emitted or absorbed obeys very simple relations. This is the formula for hydrogen, the simplest atom. This is the so-called Rydberg formula. It simply says that 1 over the wavelength of light absorbed or emitted is proportional to the difference between the inverse square of the orbital numbers that the electron starts from and ends up at. So m and n are integers just characterizing which orbital the electron is in. The ground state orbital is orbital number 1. This is equal to the energy difference between the two orbitals divided by Planck's constant times c. The constant of proportionality here, Rydberg's constant, is equal to about 10 to the 7 meters to the minus 1. So if you pass light through a gas of atoms or ions, then light at exactly the correct frequencies can be absorbed. Similarly, a gas of atoms or ions, some of which are excited, can release light at very specific wavelengths or frequencies. One way that electrons can get excited that is important in astrophysics is by collisions. If you have a gas of atoms or ions, especially if they're at high temperatures, they're moving around very fast, they collide with each other, and their kinetic energy gets transferred to energy to excite the electron up an orbital. That atom can then de-excite by emitting a photon. So then there are 3 possibilities. The first possibility is you could just get a continuous spectrum. The second possibility, and this occurs when you just have a light source, a perfect black body light source, and nothing in between it and the observer, you. If you have some gas in between the light source and you, then the atoms and ions in the gas will absorb light at very specific wavelengths. And when you take the spectrum, you will see the continuous spectrum, but you'll have certain wavelengths that are dimmer than they should be. That's because they've been absorbed. Alternatively, if you have a gas of atoms or ions that have been excited somehow by collisions or by electric current, then when the electrons jump back down, they will release light at very specific wavelengths. So when you take the spectrum, you will only see light at very specific wavelengths. This is how on Earth neon and argon lamps are made. They contain neon and argon, which get excited by electric currents, and when they de-excite, they emit very specific wavelengths or colors of light. Now, even in hydrogen, there are a large number of possible absorption and emission lines, because an electron can start off in the ground state and jump up to the second orbital or the third or the fourth and so on, or vice versa. It can jump down from second, third and fourth to first, or it can start off in the first excited state and jump up to second, third and so on, and vice versa. Depending on the start or end point of the electron, you get different series of lines. This is the Balmer series, the series of absorption or emission lines that appear in the visible part of the spectrum. The Lyman series of lines appear in the ultraviolet, and at longer wavelengths you get the Paschen series, where the electron either starts or ends up in the second excited state. So already for the simplest atom you get a wide range of possible absorption or emission lines, the Balmer series of which is in the visible part of the spectrum. If you add a second electron, that has 2 effects. It gives you a large number of additional possible transitions and therefore possible absorption lines, and it shifts the energy levels slightly, and so the absorption and emission lines occur at slightly different different wavelengths. This is also affected by the charge of the nucleus. The end result is that every single element and every single ion of an element has its own absolutely unique absorption and emission spectrum. And this is great. And that absorption and emission spectrum is as unique as a fingerprint and can be used to identify the elements and the ions of those elements present in any gas, which is great because it gives us a way of identifying what stars are made of. So when do we see absorption or emission lines? Well, there are a couple of rules of thumb, which are known as Kirchhoff's laws of radiation, not to be confused with his laws about electric circuits. The first one is just that any object radiates a continuous spectrum. The second one says that a low density gas that is excited to emit light will do so at specific wavelengths and produce an emission spectrum. In astrophysics, atoms are excited by collisions, and the hotter the gas, the more kinetic energy the atoms have, so the more the electrons are excited. So you tend to see emission spectra from gas that is low density and hot. On the other hand, if the gas is low density and relatively cool, and light from a continuous spectrum passes through it, you're going to end up with an absorption spectrum. And these three possibilities are outlined in this figure below. So where does sunlight actually come from? Well, here's a cross-section through the sun. We're not going to go into the interior at the moment. That's for later weeks. The light that we actually see from the sun comes from the photosphere. The photosphere is effectively the surface of the sun. And it is that part of the star that is at low enough density that photons can escape from the gas, that can stream freely out through space, and some of them end up hitting Earth and hitting our eyes and our telescopes. Below the photosphere, the gas is so hot and dense that light is essentially trapped. The photons bounce around and scatter off the electrons and ions. The absorption lines in the spectrum come from the photosphere, so that very last layer of atoms and ions are the ones that are absorbing specific wavelengths of light before it streams freely out into our instruments. Emission lines, on the other hand, come from the layer of gas above the photosphere, known as the chromosphere. This is very hot, up to millions of degrees Kelvin, and very low density. You can think of it as the sun's atmosphere. And that is because it is hot, the electrons are very excited and so emit a lot of light. So you'll get an emission spectrum from there. So this is the solar photosphere taken through a telescope, the familiar disk of the sun. If you take its spectrum, then you get what we saw as this yellow spectrum before. If you look in more detail and separate just the visible part of the spectrum out, you see that there is an astonishingly rich variety of absorption lines, telling us that there is a huge variety of ions and elements present in the atmosphere of the sun. So this is a spectrum taken in the similar way that you would take a prism and split light up. Here we're splitting the visible part of the sun's light up into its constituent wavelengths, and we see all these wavelengths that are a lot dimmer than they should be, indicating where light is absorbed. Another way of displaying the same information is to plot the intensity of light versus wavelength. So the green line here, the green data here, is the total solar spectrum in the visible part of the spectrum. And you can see that the green line is the black body spectrum that most closely follows the actual spectrum. So you've got a black body spectrum, but on top of it, you've got all these absorption lines. If you subtract off the black body spectrum, then you get the red spectrum up here, which just shows the absorption lines. This way of plotting it gives you a bit more information because the absorption lines don't just appear as black lines in the spectrum, but you can actually see exactly how much light is missing at particular wavelengths. So you can see that some of the absorption lines are deeper, and so more light has been absorbed, and some of them are weaker. And this tells you the relative concentrations of each element or ion in the atmosphere. And you can see when you look at the full spectrum of the sun that there are a huge number of absorption lines. And you can see some of them are marked out: calcium, iron, magnesium, hydrogen alpha, potassium, phosphorus 11, phosphorus 10, phosphorus 9. These are ionization states of phosphorus. So we can begin to put together what elements are present in the sun's atmosphere. It should be noted that although all of these elements are clearly visible in the spectrum, hydrogen is still the dominant element in the sun's atmosphere. We'll talk about the relative concentrations of elements a little later on. The solar chromosphere we don't usually see because the solar photosphere is so much brighter. But if you measure the emission spectrum from the chromosphere, then you can plot it either like the top spectrum here, where you just see the light at particular wavelengths and no light everywhere else. You've just got the emission lines here. Or again, you can plot it as intensity versus wavelength, and that gives you the relative brightness of each line. And you can see that in the chromosphere, the hydrogen alpha emission line is particularly prominent. That means that if you put a filter on front of your camera or your telescope that filters out all wavelengths of light except this very specific wavelength here, and you take a photo of the sun, you will end up just taking a photograph of the chromosphere, and that is how this picture was obtained. Okay, we'll end up with a couple of other pieces of information that spectra provide us. Absorption and emission spectra come from gases of atoms and ions that aren't just sitting there at rest, they are of course moving about randomly. Atoms and ions that are moving away from us will emit or absorb light that is redshifted relative to the wavelength of light it would emit if it were at rest. Redshift means that it's emitted at a slightly longer wavelength, whereas atoms or ions moving towards us will emit light that is blue shifted at a slightly shorter wavelength. Since there are billions upon billions of atoms moving in random directions, the actual emission line that we see will be an average of all those possible wavelengths. So what we'll see is instead of a very thin emission line or absorption line at a specific wavelength, we'll see it actually broadened. So it will contain light at slightly longer wavelengths and slightly shorter wavelengths than the wavelength you would get if every atom or molecule was just sat there at rest. The width of the line in wavelength, delta lambda here, divided by the wavelength at the central point, is actually proportional to the square root of the temperature of the gas. Because if the temperature is higher, then the kinetic energy is higher, and then the speed of the molecules on average is higher, and the redshift and blue shifts will be greater. So if we can measure the broadening, if we can measure the so-called thermal line broadening, then we can measure the temperature of the gas. This is a way to get an independent measurement of the temperature of the surface of stars. Another type of broadening occurs because when atoms collide with each other, they slightly distort the energy levels, and that has an effect of broadening the lines. This is called pressure broadening because it depends on the pressure and density of the gas. The higher the density, the more often atoms and ions collide, and you get broader lines. Density of a gas depends at its surface on its surface gravity. Surface gravity is just the value of little g, the acceleration due to gravity at the surface of the star, and that is proportional to mass divided by radius. So therefore, if you measure how much lines have been pressure broadened, then you get a measurement of mass divided by radius, and so you get some information about the mass and radius of the star. So you can see that spectral lines contain a wealth of information about the chemical composition of a star, about its temperature, about its mass, and about its radius. And we can measure it all just by carefully taking the spectrum from a star. Here's another set of spectra from stars that have similar composition but different surface gravities. We'll learn about these classification numbers next week, but as we go from top to bottom, we're going from stars with lower surface gravity to higher surface gravity, and these absorption lines are getting broader, and they have a characteristic shape as well. This shape is helpful to identify these lines as pressure broadened lines, as distinct from thermally broadened lines, which have a Gaussian shape, a sort of bell curve shape. So that allows us to tell the two types of broadening apart. The exact mathematical forms of these lines are outlined in the textbook reading this week.
So we can add to the chart that we put together last lecture. We can now measure not just the black body spectrum, but on top of that is overlaid the emission and absorption spectrum, and we can measure the wavelength and shape of emission and absorption lines. And these give the chemical composition of the outer layers of the star and information about the mass to radius ratio of the star. And of course, if we have already extracted the radius of the star, then if we know the mass to radius ratio, then it is very straightforward to extract the mass of the star. So this is another way to determine the mass of the star. And this is important because the first way to determine the mass of the star, which we learned in the last unit, is to measure the properties of the orbit of two stars, a binary system. Now, although a large fraction of stars are members of binary systems, there are many, many stars that are not. This also gives us a way to check or calibrate other methods of measuring the mass of stars. And in astronomy, it's very important that we find multiple different methods to measure the same properties of the stars so that we can check our measurements, check the various methods against each other, and make sure that we are building a consistent picture of what stars really are like.